This is video 156 for Financial Math for Actuarial Exam 2. I'm going to say right at the outset here that you should watch videos 154 and 155 before this one. I'll put links in the upper right corner here. We're doing a star problem from Broverman, 7.1.7. It's a little extra challenging. Theoretical, it's going to be a long video here. We're going to be finding limiting values of the Macaulay duration of a coupon bond using the formulas we've developed in the last couple of videos. And I do want to think about the financial meaning of these formulas and the limiting values. So that's something extra you're going to get in this as well. Here's the problem statement. We're going to emphasize that the Macaulay duration really does depend on three variables here: the coupon rate R, the number of coupon payments N, and the yield rate J. This is a function. It's the Macaulay duration of a bond with face amount F and redemption value F. That's assumed in the background. Turns out the duration doesn't depend on F. It's got N coupons at rate R per coupon period and yield rate J per coupon period. R and J are both assumed to be, in the usual situation, positive. What do we want to find? We want to find some limiting values, essentially. Find, part A, the limit of the Macaulay duration as n goes to infinity. Actually, we've already done that in the last couple of videos. Part B, the value of dr1j, let n equal 1. Now the book actually writes this as a limit as n goes to 1, and that's why I've modified the problem. You know, n is a discrete variable, so it really doesn't make sense to say what's the Macaulay duration if you have 1.2 coupon bonds, for example. 1.2 coupons. So it's not really a limiting value, though you could calculate it as a limit if you wanted to. N is a discrete variable, not a continuous variable. C, the limit as R goes to infinity, the coupon rate. You know, that's not a real practical thing. Very rarely would you have a super high coupon rate. More practically, we can think about the limiting value as R goes to 0. And actually, this is the same as the value of the function at R equals 0. I could have written this one as d of 0, n, j. You can plug in R equals 0 into these formulas, and you're not dividing by 0. Part E, let j go to infinity. Again, that's not real practical. The yield rate would hardly ever be a super high number. And finally, part F, the hardest part, the limiting value as j, the yield rate goes to 0. And I'm making an extra note here that L'Hopital's rule is going to be used for this last part, and in fact twice. We'll see that we have to use L'Hopital's rule twice for this last one. So that's the hardest one. Some extra directions as well in what you see here. For parts A through E, we're going to use the formula that you see right here. That was from video 155, the last one. And for the last part, it's going to be better to just write it as one fraction so we can apply L'Hopital's rule. We're going to use that formula from video 154. So again, you should watch those videos first. All right, here we go. Part A, again, I've talked about this already. Use this formula. What happens to this expression as, as n goes to infinity, as the number of coupon payments goes to infinity, gets very, very large, you might say, technically without bound, but you can intuitively think of it as what's happening as n gets very, very large. This part is a constant function of n. It approaches itself, 1 plus j over j. What about this part? I did mention this in the last video, though I didn't quite emphasize something as I should have. It is a function of n that's a linear function of n on the top and an exponential growth function of n on the bottom. Technically speaking, to verify this goes to 0, as it will, we probably should use L'Hopital's rule there as well, though it would be pretty tricky. I don't think I want to do that. I'm going to save L'Hopital's rule for part F. This is an exponential growth function in the bottom because j is positive, so 1 plus j is bigger than 1. Definitely goes to infinity much faster than a linear function of n does. Definitely, this whole fraction approaches 0 as n goes to infinity. And this then all equals, as I mentioned before, 1 plus j over j, which you can also write as 1 plus 1 over j. Okay? Does this make financial sense? Well, maybe not the precise formula, but if you think about its graph as a function of j, so this is the duration as a function of j, really a limiting value of the duration. As n goes to infinity, it's going to be close to what the duration is when n is very, very large. Graph this as a function of j. It's got a horizontal asymptote at 1 and a vertical asymptote at j equals 0. The graph is going to look like this. And so what this is telling you is for very, very large n, the duration is going to be very close to 1 when j is large, for one thing. Got a lot of coupon payments. If j is really large, it doesn't matter. The present value of the coupon payment for the first payment vastly outweighs the present value of the coupon payments for later payments. Because j is so large, so those present values get really, really small. That's the intuition. Remember, the duration is a measure of kind of the average time of payment weighted by present values of those payments. And so this is saying the first payment at time 1 is weighted much more heavily for large j than later payments are, because the present values of those later payments are so small. On the flip side, if j is really close to 0 and n is large, the duration is really high. Excuse me. n is large, you got a lot of coupon payments. J is close to 0, the present values are not going to be affected much by later payments. The present values are going to be relatively even, so the duration is going to be relatively large. Okay, so that makes some financial sense. On to part B. dr1j is what we want to find, right there. Plug in n equals 1. You got one coupon payment. It's occurring at time 1, the same as the redemption value. Remember, the duration is a weighted average of times of payment. The answer should be 1, right? Because you only have one payment at time 1. It's not immediately obvious that the answer is 1 by this formula. Let's go ahead and plug in n equals 1 here and here and see what happens. Plugging in n equals 1 on the top of the fraction gives you a plus r minus j, and you can see those j's will cancel. Plug in n equals 1 down here gives you a 1 plus j to the first, which is just 1 plus j, then minus 1, and those 1's will cancel. So the j's cancel here, the 1's cancel here. You can factor out a j out of the bottom here, like this, and you're left with what? You're left with a 1 plus r. And on the top, you were left with a 1 plus r as well. This will cancel with this. This cancels to a 1, so you're left with 1 plus j minus 1 over j. The 1's cancel, leaving you with j over j, which is 1 since j is positive, just as expected. Okay, so that makes good sense as well. Part C, the answer is more complicated for part C. What's the limit as r goes to infinity? Again, this doesn't have real practical importance because the coupon rate would, in real life, it's never even typically above 0.1, much less a million or something. Let's go ahead and think about it anyway, because we're told to, partially, and just because it's fun to think about. So now we're going to, once again, think about dr and j, letting r go to infinity. Look at this expression, let r go to infinity. What does it approach? Once again, this doesn't depend on the variable. It doesn't depend on r in this case. So it approaches itself, 1 plus j over j. But what about this thing? What kind of function of r is this fraction? It's what we call a rational function of r, a ratio of two polynomials in r, both of which are, in fact, linear, first power. The coefficient of r in the top is n, and the coefficient of r in the bottom is this thing, 1 plus j to the n minus 1. I hope you remember from pre-calculus or calculus that when you have a rational function where the degree of the top and the bottom are the same, 1 in this case, that as the variable goes to infinity, the limiting value is the ratio of the coefficients of that variable, n divided by this. I'll go ahead and write that down, n divided by 1 plus j to the n minus 1. And this, what you see here, is one form of the answer. Another form you could obtain by subtracting these fractions, by getting your common denominator of j times this thing. I'd have to multiply the top, 1 plus j, times this thing, and then subtract n times j, and then write that common denominator like this. You could write it that way. You can also expand out the top and the bottom for that matter. You could write it as 1 plus j to the n plus 1 minus 1 plus j minus nj. You could combine those terms involving j if you like. There are lots of different ways you could write this answer. Okay, but you can't really write it in a much simpler way. So as far as making financial sense, you can't really predict the formula without calculating it. Any of these answers is okay. Probably what's more important is, does it make sense if you graphed it? And I did take the liberty of doing that ahead of time before I made this video to see what happened to the graph. For example, if you think of the duration as a function of j, in this limiting value, I should emphasize it is again as r goes to infinity here. For very high coupon rates, meaning very high coupon payments then, the graph of this as a function of j for fixed n is decreasing, just like over here. Okay, and I'm not saying what n is, so this is not necessarily having a horizontal asymptote at n equals 1 like it did here. It's decreasing. Larger j's again mean smaller present values for future payments. So you get a smaller average time of payment, a smaller duration. What happens as n increases in this picture? Number of coupon payments increases. It should make sense the graph goes upward. It's still decreasing, but it goes higher. As n increases, the graph is higher. The duration is higher, but it's still a decreasing graph. Okay, this is saying the graph goes upward like that as n increases is what this notation means. How about as a function of n for fixed j? Well, first of all, remember n is a discrete variable, positive integer, 1, 2, 3, 4, 5, 6, etc. So if you're going to graph it, technically you should not draw a curve, though sometimes people go ahead and connect the dots anyway. You get a graph that looks about like that, increasing, concave down, you might say, even though we're not connecting the dots. And actually, when n is 1, the duration is 1. And what happens, that's for a fixed j, what happens as j increases, as the yield rate increases? Just like this graph goes down, these points should go down as well. So you get a graph that is lower as j increases. Okay? And even though the precise values can't be predicted without this formula, these graphs, in a general sense, you should be been able to predict the behavior of the graphs. On to part D. A more practical thing, what's the limiting value as r goes to 0? And in fact, that is, like I said here, the same as the value when r equals 0. It is a continuous function of r. You can plug in r equals 0. I could have stated the problem to say find d of r and j when r is 0. That's essentially what I'm writing here. So if r is 0, think about this financially. The coupon rate is 0. That means the coupons are 0. It's not a coupon bond. You're just getting the redemption value. It's a no coupon bond. So the duration should be n. It should be the time of the redemption value. This should equal n. Does it? Go ahead and plug in r equals 0 again once this becomes 1 plus j over j, just like always. What happens when you plug in r equals 0 here? You get, let's see, 1 plus j plus n times 0 minus j is minus nj. And the bottom, when r is 0, this goes away, and you're just left with j. Hopefully this all cancels to become n in the end. Yeah, if you subtract these fractions, the 1 will cancel with the 1 there, the j will cancel with the j there, the two minus signs cancel, leaving you with nj on top divided by j, which is n. J is positive here, we're not dividing by 0. Just like we predicted. This makes financial sense. On part E, what happens as j goes to infinity? Okay, again, let's think about it financially. If you have a really, really high yield for fixed R and N, what should the duration be? Again, that first payment is going to be the bulk of the present value. You should expect the duration to be close to 1. And in the limit, it does equal 1. drnj, what does it approach as now, again, r goes to 0? Look at the formula. Once again, that doesn't depend on r. I can write, oh, excuse me, we're letting j go to 0, sorry. We're in this one here. Sorry, j go to infinity. We're in this one here. J is really, really large. What happens to this thing? That does depend on j, and j is the variable now. This approaches 1, right? It's a rational function of j where the degree of the top and the bottom are the same. As j goes to infinity, it approaches the ratio of the coefficients to the highest power. 1 over 1 is 1. What about this thing? If n is bigger than 1, if n is 2 or 3 or 4 or 5, etc., this is a rational function of j where the degree of the bottom is bigger than the degree of the top. Certainly then, when n is bigger than 1, this fraction approaches 0 as j goes to infinity. That's certainly true if n is bigger than 1. What if n equals 1? What happens if n equals 1 so the degree of the top and the bottom are the same? If n equals 1, what does this become? At the top, you get 1 plus j plus r minus j. The j's cancel, you're left with 1 plus r. And on the bottom, when n is 1, you get 1 plus j minus 1. The 1's cancel. You get rj plus j. And what are we doing here? We're letting j go to infinity. Initially, we thought, when n was bigger than 1, we were thinking of these as functions of j where the degree of the top and the bottom were the same, where the bottom had a bigger degree. It turns out that when n is 1, as functions of j, you get cancellation on the top. And so we still are in the situation where the degree of the bottom is bigger than the degree of the top as a function of j. This still goes to 0 as j goes to infinity, even in the case where n is 1. So this calculation is still right, even when n is 1. All right, we're now on to the last part. Long video here, hang on with me. Now we want to find the limit as j goes to 0 of this thing for fixed r and n. It will be a kind of unexpected, complicated function of r and n, but sort of like how c was unexpected. You would never expect that answer. But once again, we'll be able to think about graphs as far as why it makes financial sense. We are going to use this formula so that we can apply L'Hopital's rule. So I'm going to go ahead and write the limit sign this time. I'm letting j go to 0. And I'm just going to write out the fraction that I showed you there. We are thinking of this now as a function of j for fixed r and n. In order to use L'Hopital's rule, we should first verify that this is what's called an indeterminate form. In this case, it looks like it should be a 0 over 0 indeterminate form. Is it? Do both the top and the bottom approach 0? Certainly the bottom approaches 0 because you have a factor of j in each thing. The bottom, in fact, equals 0 when j is 0. What about the top? These two things equal 0 when j is 0. These don't, but do they cancel? When j is 0, you get r times 1 to the n plus 1, which is r. And when j is 0 here, you get minus r. You get r minus r. It cancels to 0. This is a 0 over 0 indeterminate form. And I know with my students, that's one thing they typically fail to check when they're thinking about whether they should use L'Hopital's rule or not. L'Hopital's rule does not apply in many situations. You can't always use it. What does L'Hopital's rule say to do here? It says to try to calculate this limit by calculating a new limit of a new fraction where the numerator, the top of the new fraction, is the derivative with respect to j in this case of the top, the original, and the bottom is the derivative of the bottom of the original fraction, the denominator. Okay, so differentiate with respect to j. So this is a function of j. I have to bring, it's a power function of j. I have to bring down the n plus 1. I'm going to get r times n plus 1 times 1 plus j to the n. Technically, the chain rule comes into play as well. You got to take the derivative of 1 plus j, but that's just 1. That makes it easy. This thing as a function of j has derivative minus r. This thing has derivative minus nr. And this thing as a function of j has derivative plus 2nj. In the bottom, we are going to need the product rule here. We've got a product this times this, as well as the chain rule, though the chain rule again comes across in a trivial way. The derivative of r times j with respect to j is r. That's the derivative of the first function times the second function, plus the first function, rj, times the derivative of the second, n times 1 plus j to the n minus 1, minus r is the derivative of this one, plus 2j is the derivative of this one. Okay? If this limit exists, then it will equal what this limit is. Though both of these limits will be the same. The original limit will equal this one if this one exists. But does this one exist? This is, once again, an indeterminate form. We have to use L'Hopital's rule again. It's not obvious. Again, replace j with 0 and see what happens. You get a 0 there and a 0 there. You get an r times n plus r and a minus r minus n times r. Those cancel with 0. And on the bottom, you have an r here and a 0 there, a minus r there and a 0 there. You ultimately get r minus r. You get 0 on the bottom as well. And this is then a 0 over 0 indeterminate form, just like before. 0 over 0 indeterminate form. So we can use L'Hopital's rule again. Now, when you get to this point where you have to use L'Hopital's rule a couple times, you start wondering, okay, am I going to have to use L'Hopital's rule forever? There are situations where you can keep using L'Hopital's rule and it never helps. But in this case, it's going to help. We are going to be able to finish the problem. I have to differentiate the top and the bottom again with respect to j. Again, I'm not using the quotient rule. I'm differentiating the top and the bottom individually. That's another common mistake people make when they use L'Hopital's rule. They think they're using the quotient rule or something. It's not. Once again, differentiate this, bring the n down. I get r times n plus 1 times n times 1 plus j to the n minus 1. Differentiate these with respect to j, you get 0. Differentiate this, you get plus 2n. On the bottom, differentiate this, gives me rn 1 plus j to the n minus 1. Differentiate this with respect to j, got to use the product rule again. I get an rn times 1 plus j to the n minus 1. I also have a plus rjn times n minus 1 times 1 plus j to the n minus 2. Double check my work. And then this is minus 0 when I differentiate, then plus 2. And this does have a limit as j goes to 0. It's not an indeterminate form. We don't get 0 over 0. What does the top go to? When j is 0, this becomes 1 to the n minus 1 is 1. We get rn times n plus 1 and then a plus 2n. On the bottom, this becomes a 1, this becomes a 1, this becomes a 1, though we do have a j there, so this actually becomes a 0 there. We get rn plus 0 plus 2. In the end, we could write our answer as rn squared plus rn plus 2n divided by 2rn plus 2. And that is the correct answer. Just double checking things here. Yeah, that's the limiting value. That is the answer for part F here. The limiting value of the Macaulay duration is the yield rate goes to 0 in terms of R and N. Again, an unexpected result. Not something you could easily financially interpret. But just as in part C, we could make graphs and think about what's going on with those graphs. And the graphs are, in fact, pretty similar. If you graph the duration, the limiting value of the duration as j goes to 0 as a function of r, it's a decreasing function of r, just like it was a decreasing function of j here. Higher coupon rates give you higher coupon payments, and that in effect gives you smaller durations because for example, the redemption value is not necessarily relatively big, present value-wise, with respect to earlier coupon payments. So you get a smaller average time of payment. You get a smaller duration when r is higher. And just as before, that's for fixed n. As n increases, the graph goes up. You get different graphs that are higher. And something kind of similar happens with the duration as a function of n for fixed r. Again, that's a discrete graph that goes to the point 1, 1. And it does go up just like before. I think if I can recall correctly, it's straighter than this graph was. This one was a more concave down shape. And just like before, the graph goes lower downward here as, now in this case, r increases. Okay? And again, that should make financial sense. Larger coupon payments are going to mean shorter durations. Okay? So that was a pretty long and complicated video, but I hope you learned some things and learned how to think about these things financially too.